Hey guys, welcome back to chapter 14. In this video, I'm just going to walk you through another rate law problem. So how to determine the order of the reactants, putting the rate law together, and then again, solving for K. So just another opportunity to practice. At this point, I would hope that you guys are getting comfortable with these problems. So what you might want to do is pause the video, work it out yourself, and then watch me do it and make sure that you're following the same steps that I would follow. So here's our problem. The reaction that we're going to look at is 2NO2 reacts with F2 to produce 2 molecules of this guy over here. Here is our experimental data. So we did 3 trials. And remember, each trial we had a different amount of the initial concentration. So we either changed NO2 or we changed F2. And then we took the rate of that reaction. So somehow we reached in and we measured the rate of that reaction. So here's the 4 things that I want to do in this video. I want to first determine the rate order for each of the reactants. Once I know that, then I can write the complete rate law, think about the overall reaction order, and then finally solve for that rate constant K, keeping in mind the units for K. So let's get started. So the first step is to determine the rate order for each of the reactants. So the first one I'm going to do is NO2. So I need to find 2 trials where NO2 changes, but the other reactant stays the same. And look at there, trial 1 and trial 2 are perfect for us. So F2 stays the same. We change NO2, so those are the trials we're going to look at. And again, I always put the bigger number on the top just because it gives me whole numbers rather than fractions. But if you flip-flop them, it'll still get you to the same answer. Okay? So I'm going to take trial 2's concentration divided by trial 1 concentration. And remember, we're solving for Y, so Y is going to tell us the reaction order. Oops. And then I'm going to take the rates, so the rate of the second reaction over the rate of the first trial or first reaction. So 0.0044 over 0.0011. Okay. So I plug this into my calculator. I don't, some of you may see it here. Some of you may see it at the next step, and that's fine. So plug it into my calculator, 0.02 divided by 0.01. And I get 2y equals, plug this side, 0.0044 divided by 0.0011. And we get a 4 over here. So at this point, you should probably see that y equals 2. So 2 squared is 4. So NO2 is a second order. So I'm just going to put that in a different color so it kind of stands out to me. Second order. Okay. Now I need to determine F2. So again, I need to pick 2 trials where F2 changes, but NO2 stays the same. So I see in trial 2 and 3, NO2 stays the same, and oh good, in trial 2 and 3, F2 changes. Okay, so just do the same process here. I'm going to take trial, oopsies, gracious. I'm going to take trial 2 over trial 1. Oh, I put extra 0 in there. 0.6 over 0.3 to the y equals, and now I'm going to look at the rates. And I see that the rates are the same. The rate doesn't change. So that should jump off the paper. But if it doesn't, if you're just kind of humming along and putting numbers in and not thinking, at this next step, it should show itself. Okay, so 0.6 divided by 0.3 gives me 2y. And these 2 divided by one another is 1. So anything raised to the 0 power is going to equal 1. So in this case, y must equal 0. So this is a 0 order. Okay. So that's the first step, is determine the rate order for each of the reactants. Now that we know what the rate order is, we can write the complete rate law. So that's going to look like this. Rate equals K times the concentration of NO2 raised to its order times the concentration of F2 raised to its order. So this is step 2. This is the complete rate law. Now we want to think about the overall reaction order. So remember, the overall reaction order is simply adding up the orders for all of the reactants. So in this case, we've got 2 plus 0. So the overall is a second order reaction. Okay. Why is it helpful to think about this? Well, remember, we have this handy little tool. We have this units for K. So if it's a second order reaction, our units for K should look like this. Molarity -1, seconds -1. Remember, another way to write that is 1 over molarity times seconds. Okay, so it just gives us a glimpse at what our unit should be. All right, so the last thing here is we want to solve for the value of the rate constant K. So solve for K. So we're going to use our equation here. And again, we just pick a trial. It doesn't matter which one. We pick a trial and we just start putting the numbers in. So usually you guys pick trial 1. So that's what I'm going to pick. So the rate for trial 1 is 0.011. So 0.011 molarity over seconds equals K. That's what we're solving for. Concentration of NO2 in trial 1 is 0.01. We're going to square that. Concentration for F2 in trial 1 is 0.6. And we raise that to the 0 power. Okay. So first thing I'm going to do is just clean up this right-hand side a little bit. So just rewrite the rate. That equals K. 0.01 squared equals 1.0 times 10 to the -4th. And then 0.6 to the 0 power is again just 1. Oops, I got lazy with my units. Let me come back and get this. So these are concentrations. So when I square that, it becomes molarity squared, and then anything raised to the 0 power is just 1. Okay. So now I'm going to divide by 1.0 times 10 to the -4, molarity squared. And again, multiplying that by 1 doesn't change it. Divide by 1.0 times 10 to the -4th, molarity squared. Okay. Our units here, let's follow those through. I've got molarity on top, molarity squared on the bottom. So one of those is going to cancel. So I'm left with molarity on the bottom, seconds on the bottom, and that's the unit we were expecting. Now we just need to plug this into our calculator. So 0.011 divided by 1.0 times 10 to the -4th, and we get 110. Okay, and again, another way to write the units here, 110, -1, -1. So this is just the opportunity to practice another one of these problems with you guys. In lab, we're going to get all kinds of kinetics data, and then we'll get a whole lab period to just crunch numbers together. So hopefully by the end of that, this will be crystal clear. I hope you guys found this helpful.